Start.
test 1 2 3 เสียงมาครับ alright Shavin Chaisit has written his name in Zoom, right? So I'm gonna need to capture his signature and send it to you, right? Okay. Yes, we arrive at the alpha decay, right? It's the first example about alpha decay. Yes, I have prepared something more, right? So let's go further. นะครับมีที่ Streamlab นะครับ Shavin ครับ OBS is fine, right? For you M604 is this file, right? Say 47 as I can remember. Yes, this one. Okay, alpha decay. Okay, alpha is the nucleus, right? The heart of helium nucleus, right? So yes, it's the main part, right, without any electron. Okay, yes, we arrive at this example in we're gonna need to calculate something, right? I hope everything is fine. You could see well. Let me check what you could see from this one. Yes. Yes, the alpha decay is the separation of big atom like radium here, radium 226, right, 226. That's the number of total nucleons, whether they are protons or neutrons, right? And the atomic number, the number of protons is 88, and they have provided the atomic mass, right? Atomic mass as 226. Okay, 226.025402, and the unit for this is in atomic mass unit. Okay, it's in U unit. All right, and the outcome, and as you may have ever seen previously, let's get back to 47. Okay, here, yeah, the model is that we have radium 226, right, which is this nucleus, and what we get is two particles, which are the daughter nuclei radon 222, 86, and the alpha particle, right, the nucleus of the helium. Okay, in more details, the atomic mass, right, which is not mass number. Okay, mass number is 222, but the atomic mass is the more precise value to the mass of that nucleus, right, of that atom, and it's equal to 222.017571. Okay, you may go to the table and you could find or explore this value. Okay, please differentiate it. Okay, this is the mass number. Okay, when the ending word is number, it means it should be integer, but for this one it is atomic mass. Okay, the actual mass of that atom. Okay, for helium 42 is this one, right, the alpha particle, and they have provided atomic mass of alpha particle as the 4.002 and 602. Okay, it's not exactly number 4, the mass number of helium nucleus or alpha particle is 4, but the atomic mass is 4.002602. Okay, and this number, these digits after the decimal point is quite important. Okay, because they serve as dense energy. Okay, you know that EMC square, right? We cannot neglect this one. Okay, it's meaningful, the digits or the numbers after the decimal point here. Okay, that's the whole detail of this separation or the disintegration of the big radium nucleus. Okay, and what I want to know is the amount of the energy liberated in this decay. So of course, let's check. This is of course 226 if you add them together, but it seems that 00, right? It seems that this is 19, this is 25. So the mass of these two products, okay, of these two particles, the masses of these two particles are less than the mass of the parent nucleus, which is radium 226. Okay, so what does that mean? You just look at this by eyes. Okay, 17 plus 2 is going to be 19, but this one we start from the parent nucleus with 25. So 25 or 25 is greater than 19, right? It's greater than 19. So you could see that there is a mass loss or mass deficit. Okay, the mass that disappears in this separation. And what is the meaning of the mass deficit or mass disappearing? The mass that disappear is transformed to energy. Okay, and the energy could be dedicated to something like they could move, right? When they move, there will be kinetic energy, which is denoted by here Ke. Okay, Ke, kinetic energy. Okay, yes, that's the whole thing we're gonna see in this example, in this problem. Okay, yeah, they want to know the energy liberated or the energy that is transformed from the mass that disappear from this process. Okay, so the way to do is the following. You just find a mass difference. Okay, you need to find the mass difference. It's given by the mass of the parent nucleus, which is the mass of the radium 22688 here. Okay, this is the parent nucleus, and you could see the summation. Okay, the total mass, which is caused by two particles. Yeah, the total mass is the summation of the mass by radon, the big daughter nucleus, and the smaller daughter nucleus, which is the alpha particle. Okay, so because we have only two pieces of nuclei here, so the summation of the mass will be the mass of this one plus the mass of this one. Okay, it's not difficult, and the question has already given those quantities to us here. Okay, so we leave the mass of the radon, the big one right here. Okay, and we leave the mass of the helium right here as a second one, right? And we place the exact value in atomic mass unit. Okay, once you start from the Albert-Einstein relation EMC square or E delta MC square, that's the expression in the SI system, right? But for us, we have a fast way, right? We're gonna express the mass in atomic mass unit, and then we convert it by after. Okay, at the beginning, right? You know that we have the fast way to convert the mass to energy easily by using this one, right? We use this one, the fast way to convert any mass in atomic mass unit scale to the energy of mega electron volts. Okay, this is appropriate for only the nuclear physics. Okay, it's not appropriate for the for electron transition like in Bohr atom in the previous chapter. No. Okay. Yeah, we start from this process, right? The summation of two masses is going to be a summation of 222.017 plus 4.002, which is this one, the mass of helium or alpha particle, right? And you still need to multiply the difference here by 931.5. Okay. Yeah, the mass of the parent nucleus is going to be this one, right? 226.025, and you just find the difference, make a subtraction, and you multiply it with 931.5. This is the factor that converts any mass in atomic mass unit to mega electron volt, right? And you push it into the calculator or by hand, it's up to you, and you get the energy, which is the outcome from this separation, from this decay, right? Yeah, the big nucleus is separated into smaller nuclei, right? Yeah, that's the way to do that. Okay. Yeah. Okay. Yes. That's the way. Yes, the next one is that we're going to see the next example. Okay, this is quite simple, right? You just use the expression by Albert Einstein, and in the fast way, okay, you can do it in the SI scale, but it's complicated. Okay, we would not rather do that. We use the fast way. We express the mass in atomic mass unit because that's the information the equation have delivered to us, and we convert it by using, okay, after c squared 3 times 10 to 8 squared, blah blah blah, you will get this one, right? 931. Okay, please use this formula for the faster way. You can also start from the SI expression, but you will end up this value too. Okay, it might be more complicated. Okay, the next one is the next example is the beryllium, right? Beryllium 84. What is beryllium 84? Beryllium, right? Beryllium 84, no. Beryllium 84. No. Elementary, no. Here. Beryllium 84, where is here? Okay, beryllium is the fourth element on the periodic table in chemistry, right? This one, and one of the isotopes by beryllium is beryllium 84, right? Where is that? Of course, beryllium can have many isotopes. For example, they have also provided here the information of beryllium. Okay, beryllium can be beryllium 94 too. This one, beryllium 94. Beryllium 94 is would have the atomic mass as 9.012182. Okay, you make the summation of 4 and 5 here. You get okay, it's too small. Beryllium 84 is different from this table. Okay, beryllium 94 has the atomic mass as 9.012182, and the mass number, which is the number of nucleons, is exactly number 9, right? But it's not what we are going to consider in this example. The isotope that they want to see is beryllium 84, which is the very good isotope actually, because the number of neutrons is even, the number of protons is even, right? And they are equal to each other. That's very good. I mean, this this isotope is very, very, very stable. Okay. Yes, they said given the atomic mass of beryllium-84 to be 8.005305 atomic mass units, and we are gonna see the released energy when the beryllium-84 split into two alpha particles. So the way to see alpha particles, you start from beryllium-84, right? And you know that helium or alpha particle is helium-42, right? Yeah, helium-42 is the alpha particle. So you need to write down helium-42 and helium-42 here. And you can use any alphabet, right? It's the same thing. Once we say alpha, it means it's literally nucleus, okay? It's not the whole atom, right? Once we write down alpha notation. Okay, this equation should be valid when you make the summation on both sides, and they will be equal to each other. 4 plus 4 is going to be 8, and 2 plus 2 is going to be 4. So it's valid. So it's correct. Okay, it's acceptable. Okay. Yeah. The next one is that we go to the point, the question. This problem would like to know, and they want to see the liberated energy or the released energy. Okay, whatever term they are going to use, released energy or liberated energy or the binding energy, whatever word, okay, they use, that will be the same thing. Okay, that's the beryllium-84. Okay, we have this question. And you just follow this way, okay? And you start from radium and radon and alpha particle. You just make the subtraction or the mass difference between this side and this side, okay? In yeah. Then you convert it by using 931.5 mega electron volt per atomic mass units, right? In yeah, the information they have provided is the mass of the beryllium-84, okay, the mass of the beryllium-84 is 8.005. So, of course, there will be two terms actually, but because those two particles are the same, they share the same value of the mass. So we're going to have 2 times of the mass of the alpha particle 42. The mass of the beryllium is 8.005, so this one in minus 2 times the mass of the alpha particle. Mass of the alpha particle is provided here, 4.0062. You just take that value to be multiplied by number 2 here, and after that you still have 931.5. which is the conversion number, right, from the Albert-Einstein formula. And after that, you put it into the calculator, you get this value 0.094 or 0.0940815 mega electron volt. So, so what is the difference? You start from, you can see that the mass here from the parent nuclei, from the polynucleus, is greater than the mass of the outcome, okay, in terms of two particles, two nuclei. So it means there is released energy, and this released energy will be converted to some other kind of energy. For example, the kinetic energy, right? You're gonna see that. Yeah, that's the way you can get the meaning from this stuff. Where's my mouse? Okay. Okay. Yes. The next one, we go to a more complicated example. And yeah, this they consider the same thing, but this one is taken from the book number 2. The previous 2 examples are taken from the book number 1, but this one is taken from book number 2. And the value of the mass might be a little bit different because they may take the values from different sources. All right, มีใครจะเข้ามาที่ Zoom มีไหมครับ ไม่มีนะมีใช้สิทธิ์อยู่คนเดียวครับ Okay, okay, yes, I'm gonna send it to M604. 604, yes. Okay, yes, no one more, right? We go to again to our lecture. This is taken from book number 2, and the atomic mass of radium is 226, which is a little bit different, right? From the book number 1, they say the atomic mass of radium 226 is 402 at the end, but this one is 410, right? When we go to the more precise value, there might be some difference in both sources. Okay, but don't be panic. Okay, yeah, that's the thing. You might not need to worry so much. Okay, it's not so important. Okay, just let's go further. The mass of the radon 222 578, but this one is 571, right? A little bit different. And the mass of alpha particle is also different, 603, 602. Okay, but don't worry about it. Okay. Yeah, in the book number 2, they say show that the alpha emission is energetically possible. The word energetically possible means what does that mean? It means the binding energy or the energy is greater than 0 or not. Okay, energetically possible means the energy is greater than 0 or not for radium. Yeah. If it's not energetically possible, it means the energy is negative. So in that case, it will never take place. It will never happen in nature. All right. Yeah, that's the thing we need to pay attention. Okay. Let me observe something in this channel. Right. Okay. That's the first question. The second question is difficult. Okay, it's a little bit complicated. Find the kinetic energy of the emitted alpha particle. So, of course, you know that the whole picture of this decay is that we have radon as one of the output particle, and we have the alpha particle as the main point, right? The particle that we pay attention to, right? And yes, you may need to worry about that. They want to know the kinetic energy. Okay, of course, you know the mass of that one. You may need to know the speed, right? The speed of the speed of this particle, right? That will be the thing that will bring us to know the kind of energy for this alpha particle. Of course, the first one is to show whether the liberated energy is greater than 0 or not. But this problem, this task has been already solved, has been already done in this example, right? And we have used the value from the source by book number 1, which is a little bit different. But if you calculate it again by using the source from book number 2, right? We have to output to daughter nuclei, so the summation of the mass of the radon and the mass of alpha particle. We take the value from the book number 2, and this one is the mass from radon taken from book number 22, right? And yes, we would get the difference, mass difference, or the mass deficit, or the mass that losses, mass that disappear during this process, this transformation. And we convert it to energy by using the Einstein relation, right? We use the Einstein relation, and we will end up with the product of this difference and 931.5 again, and it's equal to 5.8708135. Please note that it's exactly the same once you use the information from the source of the book number 1. It's exactly the same, okay? So don't worry about the precision after several points in the decimal number here, okay? The important thing is we want to know 2040, right? We're gonna finish at 14, right? Okay, we need to know the kinetic energy of the emitted alpha particle. This is difficult actually. Okay, let's do that. We open a new page. Okay, yes, what is that? You know that radium 226, right? 226 and 88. Start from the rest, right? There is no movement, so we at the state 1 is equal to, okay, V of radon. And this is the state number 1, state number 2, and you have radon 222 and 86. Let's say it moves in this way, and the alpha particle 42 is moving to the right hand side. Okay, it's both are moving in the opposite direction. And yes, that once we have V1 at 0 here, it means momentum at the state 1 is equal to, whether it's vector or in scalar. But for the second stage, let's say V2. Okay, vector V2 is pointing to the left hand side, and vector V3 for the alpha particle is moving to the right hand side. So V2 is equal to, we cannot say it's equal or not, but it's different. Okay, we know that the momentum at the beginning P1 is 0, right? P1 is 0, so the momentum should maintain, right? Should be maintained. It should be the same. Should remain the same. So momentum at the second stage มีใครจะเข้าที่ซูมไหมครับมีไหมเอ่ยไม่มีนะรู้สึกว่าชัยสิทธิ์คนเดียวนะที่มักจะเข้ามานะครับผมจะได้ชำเลืองดูเรื่อยๆนะครับfor the momentum in the second stage, in this second scenario, should remain also the same, right? In yes, of course, momentum is a vector quantity, right? So it's vector 0. You know that momentum here, let's say if the reference for us is made with respect to the positive x-axis, right? This is going this way, we're going to say is positive. So V2 will be negative in this sense. So once we write down V2 will be momentum right here is going to be M radon times minus V2, right? The absolute is the absolute value is always positive, but once we take care of the direction, V2 is going to be negative because it's pointing in this way in the opposite direction to the positive x-axis. And momentum of the second piece, which is the momentum caused by the alpha particle. Fortunately, the velocity of the alpha particle is pointing to the right, so it's corresponds to the same direction as the positive x-axis. So it's going to be the velocity v3 is going to be positive, and this is the mass of the alpha particle, and is v3, right? Remains 0 because the momentum should be conserved, okay, to be reserved for both situations, should be the same. So yeah, we have the result from the momentum conservation, right? This one. And the next thing is we will take a look at the kinetic energy, right? Because this is the main quantity they want to know here, kinetic energy. Okay, how could we find it? Okay, how could we find it? You need to find the relation between the kinetic energy and the momentum, right? You need to find a relation to that. Okay. Anyway, we have a relation between momentum at the first stage to the second stage, right? The first scenario and the second scenario after decomposition. We need to find also the relation between energy at the first state and the second state. And of course, at the beginning, there is no kinetic energy at all. But at this stage, what we have is we have also the energy, right? The energy E, which is what we have got here, okay? That's the liberated energy, okay? And E will be dedicated to the alpha particle and dedicated to the radon nucleus, okay? And I don't know how much each will take, but this amount of energy, 4.87 mega electron volt, will be separated and divided for both particles, and they want to know the kinetic energy here for the alpha particle. Okay, so E, the energy from the calculation here, it's 4.870 blah blah blah, will be separated to the kinetic energy by radon plus the kinetic energy by alpha particle, right? That's the main thing, right? And we need to know this, and yeah, once you know this relation from the momentum here, you need to express it by using this relation to K alpha, right? So we want to know K alpha, right? In this scenario, we want to know K alpha, right? Yes, let's go further. Let's talk about the momentum in general, right? From material 4 or material 5, whenever you have seen this before. From material 4, we say that P is mv, right? Momentum, and K kinetic energy is 1/2 mv squared. So if we want to express K kinetic energy in terms of the momentum P, how could we express that? Right. You know that in order to have mv, right? You're gonna say it is 1/2 mv square. Okay, mv is not music video, it's mass and velocity. Okay, you can have mv square and but you have added 1 M above, right? You have to reduce M below at the denominator by the division of a single M, right? By a single M. So in terms of P, which is MV, so we're going to have 1/2 P squared by M. Okay, this is the relation between kinetic energy and the momentum in general. Okay, not only in nuclear physics in this chapter. This is valid for any story in physics. Okay. Yes. The next one is that we will go ahead with the value for the kinetic energy alpha here. Yes. The kinetic energy here will be the kinetic energy by alpha, kinetic energy by radon. So if we go into the detail, we will say that K Rn radon will be 1/2 momentum by radon square divided by mass of the radon, right? And in the same way, the kinetic energy of alpha will be 1/2 and momentum of the alpha square divided by mass of the alpha, okay, alpha particle. Once you have these, you can leave it right here. Okay, you can leave it right here in this the rate equation here. Okay, now we have the rate equation in terms of momentum like this. E will be equal to 1/2 momentum of radon square divided by mass of the radon square plus 1/2 momentum of the alpha square by mass of the alpha square. Okay, now we need to reduce something because P radon is not what we want, right? We have to substitute something, and from this blue equation, you can see that this is the first term is the momentum, right? It's minus M N and V2, which is the V by radon, right? And plus mass of the alpha particle and V velocity of the alpha particle equals 0. The left-hand side, the first term is minus momentum of the radon, actually. And here is the momentum of the alpha particle, actually. So it's going to be 0 like this. And once you solve this equation, you will see that P momentum of the radon is equal to momentum of the alpha particle. So once you know this, is that correct? Yeah, right. Yeah. Once you know this, you can substitute P radon by P alpha because it's the same, right? So we're gonna have on the rate equation like this, E will be 1/2, and here is P alpha particle square divided by M radon square and plus 1/2 still P alpha particle divided by mass of the alpha. Please note that these two terms are not the same because they have different denominator here. Okay, this is the mass of radon, this is the mass of alpha particle. Okay, once you know this, right, we're gonna have a common factor, which is the 1/2 and P alpha square, right? So once you have this, you could see that. Okay, now we use the mathematics scale. Okay, it's up to you whether you have good enough mathematics skill or not. Okay, that's the next thing we are gonna go ahead. Now we move the common term, which is P alpha square, right? P alpha square, which is the momentum of the alpha particle in both terms. That's the common term, and 1/2, right? And we have here, sorry. We have here 1/m radon plus 1/m alpha. That's the remaining thing. And of course, you can make the summation of these two fractions, okay, by making the common term, and you would get 1/2 p alpha square and m alpha plus m of radon divided by mass of radon and mass of alpha, right, as a product to that. It's not finished yet, okay. Yes, of course, we want to know the kinetic energy of alpha particle, which is 1/2 m alpha and v alpha square of v3. Well, the expression of the kinetic energy in terms of momentum is the following: 1/2, right? Momentum of the alpha particle square divided by m alpha particle, right? We need this term. And once we have this relation, we're going to see that if we move m alpha in front or out of the parentheses here, we're going to have 1/2 p alpha squared divided by m alpha, which is exactly the same term here, right? So we will move this term. We will move this term to be here out of the parentheses and appear as the denominator. So the rate equation here could be written as E will be 1/2 p alpha square divided by m alpha. Okay, this is the mathematical scale. Okay, you need to have it. Otherwise, you cannot go ahead with, I don't know, to be a doctor in medicine, faculty of medicine, or to any other study branches. Yes, next, the remaining term is only this one, m alpha plus m radon, right? And here we have m radon right here. Okay. Now, the red term on the left-hand side here is exactly the same as what we want, which is the kinetic energy. So, yes, right, is this correct? Yes, right, yeah, we are gonna move the blue one to the left-hand side so that we get the kinetic energy alpha. So K alpha will be, once we move this term, the denominator will appear as the numerator. The summation as numerator will appear as the denominator on the left-hand side. So we would have m radon times released energy from the previous step divided by mass of alpha particle plus mass of radon, right? You can write also mass of radon first. That's the thing, okay? Yes, of course, let's go further. Okay, there are two ways. The correct way is to use the atomic mass, right? Atomic mass, the correct way. The atomic mass, which involves so many precise value, which involves 226.025.410 and 222.017.578.4002603. You have to substitute it to this one, and E is the value here. Okay. But you may see that it's difficult, right? It's full of a lot of digits here. Another way is, this is the correct way. It is correct, okay. It is a correct way. And another way is that you just use the mass number. Okay, mass number. What is that? It means this is incorrect. Okay, this is incorrect. It's wrong. The mass number is that the way by using mass number is that instead of 226.025, you may use simply 226. You may use, instead of 222.017, you may use only 222. Instead of 4.002603, you may use only simply number 4. And we are going to see whether the incorrect way is good or not. Okay. Okay. The first way is the blue one, right? Okay. K alpha will be mass of radon is 2.017578, right? Divided by the mass of helium, which is alpha particle 0.00263 plus 2.017578 right here. And you multiply it with the energy you have got in the previous step, which is number, I don't know, let me write down here, 4.8708.135. Okay, this is the correct way. And the outcome you have got from the correct version is the following, is this one. This one is equal to 4.784 and 5560. The unit of the energy is mega electron volt. Okay, that's the correct way. That, as I said here, correct way. You just use atomic mass. The incorrect way is simple one, right? You just use only mass number. Okay, let me write out the incorrect version by using the red font here. The incorrect one will be shorter, right? You just use only mass number, which involves only integer. Okay, radon is 222, right? We are going to use 2 divided by mass number of helium is only 4, right? And plus 2. And you could see that it's easier, much easier, right? Because we don't need to write down so many digits after the decimal point. And the next one is we have to leave the value of the energy here, right? Which is the release energy, the same way, which is 4.87.08135 mega electron volt, right? And yeah, after the outcome, what you can get is 4.784 and 604 and 4 and mega electron volt. Okay, right here. So what is the difference between the correct version and the incorrect version? You could see that 4.87, 78, I'm sorry for that. Sorry, it's already correct. 4.784. It's the same, exactly the same accuracy you get here. Okay, the first 3 digits, you get the same thing, right? But after that, it's incorrect. Okay, let me point out in a different, okay, this one is different at this location here. Okay, so the wrong version by using the mass number is quite precise for only the first 3 digits, but the way to make computation is easier, right? Okay, this is the solution. This is the answer, right? Whether you both methods are valid for this situation. I show you both ways, right? Okay, yeah, that's the kinetic energy of the alpha particle you can get from this process here, right? The radium-226 is decomposed into radon-222, and one or single alpha particle, and they got the kinetic energy like this with this amount 4.784 mega electron volts. Okay, it's quite high. Okay, actually. Okay, now let's move to the next story. Yeah, you have seen 3 examples about the alpha decay, right, in numerical way, and of course, in physics we have to compare it to the realistic measurement, and the observed energy from the alpha particle is shown here. Okay, the y-axis is the quantity of alpha particle number. Okay, how many alpha particle numbers you have, so on, and this is the bar, the value of the kinetic energy you have got, which is similar thing you have seen here under the calculation, and it is found that the observed energy is not continuous. They have a certain values. Okay, the kinetic energy do not take place everywhere, only a certain value. So what is the main thing then? What is the meaning then? Because we have certain decomposition, right? So the energy will not be any value. Yeah, alpha decay come into discrete amounts of energies, because 2 dotted particles have momenta with equal magnitude and opposite direction, and each composed as a fixed number of nucleons. So it cannot be any continuous value. They are discrete values. Okay. Now let's move to the next type of decay. We still have 14:20. So we have to leave at 14. We still have 22 minutes. So let's move to the second type of decay in this chapter. It's beta decay. Okay, we start from the big decomposition, big nucleus that is composed into big nucleus like alpha particle helium-42. But this one beta decay is not a big decomposition. Okay. So what is the situation? The alpha decay will take place when the nucleus of any particle is too big, is too large. Okay, there are too many neutron proton. When the size of the nucleus is too big, the nature will in nature they will be decomposed into smaller nuclei. Like the faster way is to be decomposed into alpha particle, which reduce the number of nucleons by 4. Okay, 2 protons are separated out of the parent nucleus. But beta decay is another kind of decay that doesn't reduce so much the size of the nucleus. It's just change only one particle, one type of the particle in the nucleus or the nuclei. Okay, it is discovered somehow in 19th century, and the beta, which is denoted by the beta letter in Greek alphabet, the beta particle is known as actually electron. Okay, it's only electron. It's not, and of course you know, electron is much smaller than neutron and proton, but this alpha particle has 2 protons, 2 neutrons. So electron is much smaller than the alpha particle. So simply speaking, beta particle is much smaller than the alpha particle. Okay, but both have different destroying ability. Okay, I don't know, penetration ability. Okay, the big one cannot penetrate well. Okay, but because it cannot have high velocity, but this one has high velocity and it can penetrate because its size is small. It can penetrate through several atoms. Okay, and this one is the big nucleus, right? Yeah, that's the reason we have different type of penetration. The emission of electron from the nucleus is surprising because in our previous discussion, we see that the nucleus is composed of protons and neutrons, right? But it's not the case. Once the technology goes by, the scientist has, the physicist or the scientist has discovered something new. It can happen when, of course, you know that the big nuclei will stay well, will have a good binding force, good binding energy when the neutron is needs to be much, right? We need to have so many neutrons, and then the nucleus will stay quite stable, right? Yeah, but too much neutron will not also be good, right? Because for some reason it may not be stable at all, and the way to do that is that the nucleus try to change the neutron to be proton. Okay, so that the ratio between neutron and protons will be in a good ratio. So, and in that case, the nucleus that has too many neutrons will try to change one neutron to be proton. And once the neutron is separated into proton, they're gonna release also the electron. Okay, and you could see that electron just goes out of the nucleus of any big atom, right? This electron is not the same as the electron that's move around this nucleus. Okay, this is the additional created electron, okay, from the nucleus directly. Okay, it's not the electron that moves around this nucleus. Okay, the emission of the beta particle is caused by I say simply only proton and electron as the outcome of the product of this process. But actually, once the technology goes by, once the scientists pay more careful to this process, they have also discovered a tiny particle, which is very, very hard to detect. Okay, this one V and bar and with subscript E, what is that? Anybody know that? You have already seen this, the detail of this particle before, and it's known as, what is that? It's known as the Electron Anti-Neutrino. Okay, Electron Anti-Neutrino. Okay, let's go further. We will not talk about Electron Anti-Neutrino at the moment because it's the additional particle that was just recognized after that, because the mass of this one is very, very small. Okay, even less than the mass of the electron, and because it's neutral, it has no charge, so it will not interact to anybody, to any particle, and that's why we would say it's very hard to detect. And this particle will be explained later in the beta particle. Okay, the process here you see is considered to be beta decay, but actually we would say more precisely as, we call it more precisely as the beta minus decay, because the outcome is the electron, which is a negative charge, right? And let's go into the detail of the nuclear equation, atomic expression, right? Emission of beta particle is caused by the transformation of neutron N01. You know N01, right? On the left-hand side, this is the atomic number, which is the number of proton. Neutron has no proton, so this is 0. And on the left-hand side above here is the superposition on the left side, denotes the number of nucleon, right? So of course, neutron belongs to is one of the nucleon, right? So it's going to be it's considered to be the one of the nucleon. So that's why they have number one here on the left hand side as a superscript. For the proton, we have notation P11 because proton, of course, this is the location of the proton, right? This is the location of the proton. This is the location of the number of nucleons. Proton 1, so the particle proton, so it means we have single proton number 1 here. And proton is one of the nucleons, so we have A as number 1 here. This is Z equal to 1. Okay, this is the atomic symbol, right? It's atomic expression. And electron, what is the notation of electron? Electron is E minus, and because this is the location of proton, right? Electron is in the opposite way to proton, so it has -1, and it doesn't belong to any nucleon, so this is 0. Okay, the transformation of neutron into proton and neutron. So we can express the neutron from this process like this: 54. Okay, neutron is decomposed into one piece of proton and one particle of electron. But I would say 54 is still incorrect. Okay, we will go through this story like this. Okay, we consider first the incorrect version of this beta decay. A free neutron decays into a proton and an electron with an average lifetime of about 15 minutes. Okay, lifetime of the proton and neutron here, a proton and electron here, are about 15 minutes. To distinguish it from another particle, the positron. Okay, we're gonna use E with plus as a superscript on the right-hand side here. And the emitted particle today is called beta minus. And as I told you, this process, neutron to be proton and electron, is called beta minus decay or beta minus process. Because we want to mention the electron, okay, which has a negative charge. But there is another type of beta decay. We will talk about that later. Let's consider first when does the beta minus decay will happen. Okay, the process will take place when there are too many protons. So you know that the ratio between neutron to proton is quite important, and N by Z is too great for stability. So the nature will try to convert neutron to be proton, to change the blue one to be the red one, so that the ratio between neutron to proton will be in a good situation, in a good level, right? Once it has a good level, the nucleus will be stable, and once it's stable, they're gonna live long, right? And yeah, we have okay, for any element, this is the basic, but the fundamental neutron is decomposed, is transformed into proton and electron. But for any nucleus, that nucleus is gonna have one more proton, and one more proton means the atomic number is changed, when the atomic number changes. Once the atomic number changes, we have a new element, because this is the number of protons. When the number of protons changes, it means we have new elements. So it's no longer element Y, it's another element, which let's say it's element X. But even when you transform neutron to be proton, the number of nucleons, whether it's red or blue, they will be the same. Okay, so the A number, which is the number of nucleon here, will remain the same for this process. But the additional thing you could get is followed by 54, right? You have the electron moving out of the nucleus, and that's known in this level in physics as the beta particle, right? Yeah, beta particle will follow the same notation to electron, okay, -1 and 0 above, and negative as the negative charge on the right hand side as the superposition as a superscript. So the generic process in this generic process of the beta decay, the number of neutron decreases by 1 because we lose 1 neutron to be proton, right? Z increases by 1 because neutron is converted to proton. So we have 1 more proton. We lose 1 neutron and we get 1 more proton. Once we have 1 more proton, we have a new element. Okay, no longer Y, it's a new element X. It remains the same because the number of nucleons here will be the same, right? Whether neutron is converted to proton or proton to neutron, they still stay inside the nucleus. Okay, yeah. So the generic process have this feature in decreases by 1. Okay, number of neutron decreases by 1. 1 proton increases. Okay, and number of nucleons remains the same. And typical type of okay, this is the general expression for any element. The one thing that take place in nature is the carbon-14. Okay, carbon-14 is the radioactive isotope of the carbon. You know, carbon can be carbon-11, carbon-12, carbon-13, carbon-14. Carbon-14 seems to be the biggest one, right? We could find in nature. And carbon-14 is not the stable version of, not stable isotope at all. They have half-life like 5,730 years or something like that. Okay, in 5,730 years, the amount of carbon-14 will remain only half of that. All right. Okay. That's the thing we need to pay attention. Okay. The next one is from this equation. This is the general process, right? Generic process in general form for any element. When we substitute the actual element that takes place, we start from carbon-14. Okay, carbon has 6 protons. And one of the neutron in okay, you know that they have carbon-14 has 8 neutrons, right? And yeah, neutron is a little bit too great, right? Too much for them. 1 neutron will have to change itself to be proton, but it still stay inside the nucleus. So the number of nucleon will remain the same, which is 14. And once we lose 1 neutron and we got an additional proton, starting from 6, we have 1 more, so we have 7 proton. Once we have 7 proton, you have to go to the periodic table. Carbon with 6 proton. Once you have 1 more proton, you go to another element, which is nitrogen. So now you could obtain the nitrogen 14. Okay, nitrogen 14. So what is this situation? Nitrogen 14 has 7 protons and 7 neutrons right now. So the ratio between proton and neutron is good, right? 7 per 7, right? 1 by 1. And this will make the good situation for the nuclear force inside the nucleus of this element, to the nitrogen 14. But from the generic process of the beta minus decay, we need to have an electron of the beta minus particle electron here. Okay, so that's the whole thing about beta minus process. Beta positive decay is another version of the beta negative decay that you have seen before. Beta positive decay has been found later after the beta minus decay. What is the situation when the beta positive decay will take place. Okay, let's get back. Beta minus decay will take place when there are too many neutrons inside the nucleus. Or in mathematical way, neutron to proton is too much, too great. So neutron has to be converted to proton. But beta positive will be in the opposite way. If your nucleus has too many protons, protons has to be converted to be neutron, so that the ratio between neutron and proton will be in an appropriate level, in an appropriate value. So beta positive decay will take place when there are too little neutrons. So neutron to proton is too small. There are too many protons inside the nucleus. The nucleus has to convert a proton to be neutron for stability. So in this case, it's called proton rich. Okay. In this one, it's called neutron rich because it's full of neutron. In this one, in beta positive decay, it's proton rich because the nucleus is full of proton. There are too many protons inside the nucleus. The proton has to be converted to neutron. Okay. It's not like this one. Neutron is converted to proton. Okay. This is beta positive, and the general process is the following. Sorry. You start from the same A, Y, Z, right? The initial element, A, the number of nucleons, Z is the number of proton. And the outcome is different because you lose one proton. You have too many protons, you have to reduce the number of proton by one, okay? And one proton is converted to neutron. But you know that even the conversion takes place, it happens inside the nucleus, and the number of nucleons will not change, okay, will remain the same. So don't worry about it. So we get AXZ minus 1, okay, this one AXZ plus 1 because you got additional proton. But this one we lose one proton. We can no longer use the letter Y because once the number of protons is different, once the number of proton changes, we've got new elements, which is denoted by letter X. But the outcome is not electron anymore because if the proton is converted to neutron, it's gonna bring you the positron. Okay, positron is the anti-particle to the electron. Okay, it's the mass of the positron is exactly the same as the electron. But the charge is in the opposite way. The positron is a positive charge, okay, has a positive charge. The electron has a negative charge, 1.6 times 10 raised to negative 19, okay? And that's the general process for the beta plus decay. Note that in 57, we have ขออนุญาตเลยสัก 2-3 นาทีนะครับเนื่องจากเสียเวลาเซตเครื่องครับ and the daughter nucleus, which is the letter X, and the proton, you have n increases by 1 because proton is converted to neutron, right? You have number of neutron, one more, right? You have one more neutron. The number of proton decreases by 1 because one proton has to be dedicated himself to become a neutron, right? So one proton is missing, so Z minus 1 here. Even proton and neutron stay inside the nucleus, so A remain the same. The number of nucleon remain the same for that element. But once the number of proton changes, we have to write down the next symbol for that element. Okay, in magnetic field, the beta particle can be identified. Okay, because you get the positive charge when the conversion takes place. There will be liberated energy. Liberated energy will be transformed to the kinetic energy of this one, kinetic energy to this one. Once this one has the kinetic energy, it's going to move, okay? And when it moves in the straight line or whatever direction, if you trap it by using the magnetic field, you're gonna see the curvature of this one. And from the curvature, you can measure the radius and you can find the speed of this proton. So the proton can be identified because it has charge, right? That speed can be measured by measuring the curvature of their path, as I told you, measure the radius of the circular path of the positron. The speed of the beta could be up to 0.99995 the speed of the light, okay, which is very, very close to the speed of the light. So you cannot use the typical expression of the movement. You need to deal with relativistic expression, which is the theorem by Albert Einstein, right? So that's the whole thing, whole theory about beta decay. We will start the calculation or the example of the beta decay next time, okay, on Friday. Okay, we have 2 examples to make the calculation, and then we finish the beta decay. โอเควันนี้ก็คงจบไว้เพียงเท่านี้ก่อนนะครับแล้วก็พบกันวันศุกร์นะครับผมตรวจข้อสอบมาให้คุณแล้วนะครับทั้ง2ห้องนะครับข้อสอบซ่อมนะผ่านเป็นส่วนใหญ่นะมีอยู่คนนึงนะครับรู้สึกใครอัครวัตรหรืออะไรสักอย่างนะครับได้แค่10นะครับได้แค่10นอกนั้น20กว่านะครับก็ถือว่าผ่านแล้วผมยังไม่ได้ตรวจพาร์ท2นะครับเนื่องจากว่าต้องเตรียมต้องอะไรให้คุณเยอะนะครับก็โอเค see you on Friday สวัสดีครับบ๊ายบายครับ if you have any question นะคนที่ดู Zoom YouTube ครับ if you have any question just let me know if not then พบกันวันศุกร์ตอนเช้าครับแล้วก็คุณครูอาจารย์อะไรที่สอนคณิตเขาอาจจะมาแทน28หรืออะไรนะครับเดี๋ยวว่ากันอีกทีโอเคครับบ๊ายบายครับสวัสดีครับบ๊ายบายครับ
Known as the
เคกดชวงวัดมาแล้วนะครับ this one okay good afternoon M605 right, good afternoon M605, welcome to SCI33206, which is the physics number 4. All right, I hope that everything is fine. Same mouse too. This one thing, I don't know why I couldn't see the chat list for the OBS number 2. Okay, here. Yes, here chat list for number 2. KR, that's the symbol. KR. So it's time for us in M605, right? Let's go ahead with that. Well, most of you have started to write down your name, right? All right. Okay. Okay. For M605, we arrive at the carbon dating, right? As I remember, we arrive at the page 74, right? Instead of 47. The M605 has just arrived at the calculation of the beta decay. For you, M605, we would go to page 74, but one additional thing is this one. Okay, I need to mention to you on page 70, which is the new thing I have just found and added to our lecture note 70. We need to start the carbon dating on page 76, but anyway, two things are added in the lecture notes. Okay, after at the end of the beta decay, because you might see the better picture of everything that happens. Okay, I hope that everyone is going well, right, on so many things in YouTube channels. Anyone want to join the Zoom section? มีใครจะเข้ามาที่ห้อง Zoom ไหมครับมีไหมเอ่ยไม่มีนะ Okay, then it's no problem. When we will talk about that on we'll talk about that in the good notes only. Okay. One thing you need to see is that you have seen the alpha decay, beta decay, right? Well, I need to mention there are actually 4 series that start for the decay. The first one is uranium 238. Okay, it's a big element actually, and the half-life spans a very, very long time across our Earth, right? It's 238 เสียงมีไม่มีนะครับช่องไหนนะครับ โปรดบอกครับเสียงมีหรือไม่มีอย่างไรนะครับโอเคไม่ต้องเกรงใจนะครับ if there is no sound just let me know okay it's number 2 so it's number 2 number 2 more to you okay this is the YouTube okay yeah if you have any audio problem just let me know in any channel trying to solve it for you okay the 4 series are the following well uranium-238 which has the number of protons or the Z number has 92 and another series of uranium is called actinium. Okay, it's also uranium, but it's a kind of uranium. It's another isotope for uranium. It's also unstable version, but this would not last quite long as the first version 238. Okay, once you have more neutron, they're gonna be packed more stably, right? More stable. The half-life of the first series lasts I don't know 1,000 on the scale of 1,000 million years, so it takes very long time, and the ending points, the output that remains stable will be lead, right? Lead 206, and the lead 206 in the number of protons or the lead is 82, right? Every series will stop at lead, okay, and you could see the lead on Earth quite easily, right, everywhere, because that's the ending point of the big radioactive elements like uranium, actinium, and thorium, and neptunium. Okay, the first series comes from the big one, 238, with the number of nucleons is 92. Another big one is neptunium. Okay, neptunium denoted by NP, it has 237, and the number of protons is a little bit bigger than uranium is 93. But the half-life of the neptunium, once it has more proton, is no longer stable, right? Because it's full of Coulomb forces. The half-life of the nucleus of neptunium, okay, the amount of that radioactive nucleus will remain only half by 2.14 million years, so take a long time. Our age is on the order, our human age is on the order of 100 years. Okay, no one is much bigger than, no one would last longer, much last longer than 100 years. So we are around 80, 90, we pass away, we die. But this one take billion years, so it's take a long time. The more stable one is thorium. Okay, thorium is denoted by 232, the number of nucleons, okay, in the nucleus, proton plus neutrons. But the number of proton is a little bit lower, is 90, okay. 2 protons two protons less than uranium, because they have smaller protons, they have smaller neutron too. The half-life of thorium is a little bit longer. It's 14,100 years. 14,100 million years. Okay, take a long time, and the ending point for all of these 4 series will be lead. Okay, but it's a different version, different isotopes of lead. Okay, everyone will stop at 82 as the number of proton, but the number of nucleons might be different, and they have totally different nucleons here, the mass numbers here. Okay, 206, 207, 208, 209. Okay, in this all in this ascending order. Okay, increasing order. Yeah, that's the 4 series that take place in nature. Okay, we didn't force it. Okay, it just came up on Earth and it tried to disappear a little bit. Okay, but takes very long time, million years. Okay, that's the thing that could happen for radioactive series in nature. Okay, and no one forced them to take place. Okay, it just take place in nature. And let's consider the thorium-232, which is this family, the third family. Okay, let's see. We start from thorium-232, which has 90 protons in the nucleus. Okay, this one. And I'm not sure whether you could see well or not. Okay, there are 2 types of decay, right? You have seen the alpha decay and the beta decay, right? Alpha decay will decrease the number of nucleons by 4 and the number of protons by 2, right? Yeah, thorium go to radium, 232 thorium to radon 228. You could see that 232 is reduced to 228. So the missing nucleons are 4. Okay, there are 4 missing nucleons, protons and neutrons. That's the alpha particle, and they say that the violet arrow represents the beta decay here. Okay, and after that, 228 radon is converted to actinide. I think it's called actinide. Let's go to the periodic table. I also cannot remember. Yeah, radium to where is that? 90, right? Where is that? Radium to radium, right? To where is that? Radium to, let's open another page of this one, right? Okay. Radium to actinide 228 AC. Radium here to be the smaller one. Where is that? AC มีคนไหนเห็นไหมครับ Where is AC? Thorium? Not thorium yet. Radium is here. Right, radium. AC มีคนไหนหา AC เจอไหมครับผมเปิดเสียงนะ AC, where is that? Actinium, AC228. Otherwise, I'm gonna fight right here to not lose some time. Actinium. No, 98. 89, sorry. 89. So this one, I'm sorry for that. Okay, radium is transformed into actinium. It means the neutron. Okay, neutron is converted to proton, right? Neutron is converted to protons. That's the beta minus decay, right? So beta minus decay takes place during this route, and the lower left violet arrow is represented the alpha decay, but the blue to the lower right is beta minus decay. Okay, one neutron is converted to proton. Okay, radon is converted to actinium. This one, and later one neutron again is converted to proton. So from 90, let's see, okay, 88 to 89, okay, during this route, and 89 to 90 to become thorium, this root, okay, and this is the beta minus decay because one neutron is converted to a proton, okay, that becomes thorium. Once they have 228 thorium with 90 protons, you go further to the left and the number of nucleons are reduced by 4, 228 to 224, right? 224, so it changes again from not radium 228 to now we arrive at radium 224, okay? The same element, 88 protons, okay? Proton have been, 2 protons have been discarded or separated into alpha particle, right? 4 neutron, 2 neutrons will go away, 2 protons will go away as alpha particle. So from thorium, we get again radium 88, but the number of nucleons is reduced by 4. Okay, we get here. Yeah, that the alpha particle, okay, that is being thrown away, that is thrown away during this route. Alpha particle is emitted during this route. Now radium is moved to radon, okay, as we have seen before, to become 86. Here 88 becomes 86. So alpha particle is moved, is discarded again. Here is removed from during this is decomposed from the big radium nucleus. Okay, we arrive at radon 86 here, and the next thing is we arrive at polonium. Polonium is 84, so we throw away 2 protons, and you could see 220 remains 216. So the number of nucleons is reduced by 4. Right, the number of nucleons is reduced by 4. So the alpha is again emitted during this process. Okay, and as I said, the yellow, the violet arrows toward the lower left will give you the alpha particle laid on to polonium. Okay, and after that, during this route, we arrive at the lead. Okay. Polonium to become lead 82 right here, okay, and yeah, the number of nucleons to 16 to 212. So 4 nucleons are removed. So this means we got the alpha particle emission during this route, and after that, 222 lead, which has 82 protons, is moved to 212 to 12 bismuth. So 1 neutron is converted to proton. So that's why from 82 protons, we arrive at 83. So we have 1 more proton where the neutron is converted to proton. But once the neutron is converted to proton, it's going to exhibit the electron, right, which is the beta minus process, beta minus decay. So beta particle, which is the electron, is generated during this process. Okay, and once you arrive at the bismuth 212 with 83 protons, you could go to the left or to the right. Okay, down way. To the left hand side, you will arrive at TL. You reduce it, the number of neutrons and proton by each 2, right? 212 to 208. So you lose 4 nucleons, and 4 nucleons mean we lose the helium-42 nucleus, right? That's the alpha particle. And another route, what is TL? TL is the thallium, okay? Thallium is a kind of element here. Okay, and next one to mercury, okay, thallium. And yeah, that's the left-hand side. For the right-hand side, bismuth 83 with 212 nucleons would change one neutron to become an additional proton. So from 83, we arrive at 84, and that's the next element on to the right-hand side, and that's polonium again. Polonium here is different from polonium 216, okay, because this is polonium 212, only 212 nucleons inside the nucleus of this polonium. Okay, let's get back to the left-hand side. Once you get the thallium to 08, you can change. Okay, thallium is here. You can convert. Okay, one possibility is that you convert your neutron, one neutron to become proton, right? So the number of nucleons will remain the same because the neutron or proton will stay inside the nucleus. Number of nucleons will remain the same, 208. And but important thing is that once the neutron is converted to proton, we have an additional proton. Thallium has 81 protons. When it has one more proton, it's going to be 82. But 82 is no longer thallium. It's known as lead. Okay, the metal that you could observe everywhere on Earth. All right, that's the whole thing that happens. Okay, the polonium 212, what is that? Polonium 212 is a big one, which is here. And the big nucleus can get to the stable version, which is lead, right, 208, by throwing 4 nucleons away. And that 4 nucleons mean the alpha particle. So that's why you get the alpha particle emission from these roots. Okay, all right. And that's the whole thing. You could see what happened in this series, the thorium 232, okay, which is a quite stable version to this one. Okay, thorium 232. Okay, the gamma decay is already what M605 has considered it. Now we arrive really at the carbon dating, the next chapter for you. I know this next topic for you, M605. Okay, that's we stopped last time. Okay, that's the 2 things I have added to the lecture, but the M604 did not allow it. Okay, carbon dating is the new topic for us. In M605, there are many names for that. There are many names for carbon dating. One of these is known as radiometric dating, they can say, or radiocarbon dating. Okay, you can use these keywords to browse the information, but it will bring you to the same story here. Okay, it is really used in practice. Okay, if the people has a doubt about the age of ancient people, like the one with mummy and pharaoh and so on, right? Or any ancient stuff. Just use this nature, because anyone on Earth, anyone who lives on Earth, would face with this carbon nature in their life, because you breathe, you take breaths inside and outside your body, and the carbon dioxide or the carbon is going to be circulated in your body. If you eat something on Earth, okay, everyone who was born on Earth should have food on Earth, but otherwise you would not be able to grow up. Yes, this story really takes place on Earth, and yeah, as mentioned earlier, carbon-14 is a radioactive isotope of the carbon nuclei, We have carbon 11, we have carbon 12. Okay, carbon 12 is the standard element, a stable one, right? Stable nuclei to make the reference as the atomic mass unit, right? Carbon 12. Carbon 13 exists also in nature, but carbon 14 is very rare because it's the radioactive isotope. Okay, carbon 14 is the major thing. Okay, we have to thank to our clever scientists who mentioned this direction. Okay, because the carbon 14 is a good example, good isotope, because it's in a good scale in terms of half-life, duration, and so on. Okay, carbon 14 is unstable but with a long half-life, and if you want to observe any object in the same scale at its half-life would be appropriate. Okay, I don't think that you want to observe something in the order of billion years. Okay, it's too old. But carbon 14, which has half-life of 5,730 approximately, okay, plus and minus 40 years for the error, would be a good candidate, good isotope as the candidate for us. The half-life of the carbon 14 is 5,730 years and plus and minus 40. Okay, in our world, the carbon 14. Okay, you know that carbon is the element that has 4 protons, right? You know that carbon has the 6 protons, right? Carbon has 6 protons, and in this version the carbon has 8 neutrons. It's carbon 14. Okay, once the neutron is too much, okay, they are gonna change itself to become proton, and when the nucleus of the carbon has 1 more proton, it's no longer carbon. It's gonna be the next element. Okay, and what is the next element? Carbon. The next one, once you have 1 more proton, the element is no longer called carbon. It becomes nitrogen here with 7 protons. Okay, we cannot do that. It happens in nature. Okay. Yes. On Earth, because we have the atmosphere that protects our life on Earth, right? Yes, the carbon 14 is generated every day. Okay, in the atmosphere level, because outside our world, our Earth, there are cosmic rays. Okay, high. What is cosmic ray? Cosmic ray is the big particle, like it's also like an alpha particle too, but it is full of also a neutron and other stuff. Okay, with high energy particles from somewhere else, from outer space. Okay, we cannot do anything. Okay, that happens in nature. Oh, ผมลืมปิดไฟเดี๋ยวนี้ขออภัยครับเดี๋ยวปิดไฟ โอเคลืมปิดไฟครับมันก็จะส่อง Okay, the carbon 14 is the main feature to us in this scenario. Yes, the carbon 14 is the key feature which is generated in our atmosphere because the cosmic ray are the high energy particles from outer space. Okay, it's what's generated by sun, by other planets, by other stars, and yeah, it's because our Earth has the atmosphere that protects us, and at the atmosphere level, there are some process that happen here. And that's the generation process for the carbon-14. At the atmosphere, we have nitrogen-14, okay? And that's the remaining thing after the carbon-14 is converted on Earth, okay? We have also nitrogen, right? In our atmosphere, nitrogen-14, and once we have neutron, okay, high energy neutron from somewhere else, from other star that is moving to us here at the atmosphere. The high energy neutron will catch or touch the nucleus of the nitrogen-14, and after that, it's going to bring us the one proton, okay, and the proton is removed from this one, okay, from the nitrogen. You could see that 0 plus 7 is equal to 6 plus 1, and 1 plus, oh, I'm sorry for that, this is incorrect. เลข0ตรงนี้ต้องเป็นเลข1ครับเดี๋ยวผมไปแก้ให้นะ 1 plus 14 should be 14 plus 1 here, okay. P ต้องเป็น11นะครับ P 11 P 01ไม่มีนะผมพิมพ์ผิดนะ okay. Because usually proton should be P's 11 I'm stupid นะครับโปรตอนเนี่ยโปรตอนต้องเป็น11อย่างนี้นะครับผมพิมพ์ผิดนะอันนี้ไม่น่าดุลสมการไม่ได้ so this one is number 1, okay. 15 plus 1 will be 1 plus 14 plus 1 will be equal to 1 plus 14, and under here the number of protons, you have 0 plus 7 and 6 plus 1, right? So when neutron hit the nucleus of neutron hit the nucleus of nitrogen, right? And the proton is kicked out, okay? Proton is moving away, okay? And yeah, the neutron just stay inside the nitrogen nucleus instead of the proton, okay? It's like you have, somehow it is, you have, I don't know how to, you have proton here, right? And one more proton, okay? Other than that is neutron, okay? This is the nucleus of nitrogen. They have 7 too, right? 7 neutron. 7 neutron. 2, 6, okay. They have also 7 neutron. This is the nucleus of the nitrogen. And the cosmic ray just bring a high energy neutron, okay, moving to the nucleus of the nitrogen. This is the nucleus of the nitrogen. And the nitrogen, the neutron here just kick out the proton that stayed formerly inside the nitrogen nucleus, and one of the neutron, one of the proton is going out, and this one, the neutron, just stay in place of that location, okay, in place of that proton, okay, and this proton is going out, is denoted by P11 here, and this is the proton that is kicked out from the nucleus of the nitrogen. That's happening, okay. And with this situation, which is caused by the high energy neutron from the cosmic ray, we have got the carbon-14 in the atmosphere, okay, and carbon-14 staying out in our atmosphere. When it touches oxygen, okay, it's gonna have chemical interaction, right? They get carbon dioxide, carbon monoxide, whatever type of combination of carbon and oxygen. The main thing is carbon dioxide, but it's not carbon-12 O2, okay? It's no longer carbon-12. It's carbon-14 dioxide, but carbon here is radioactive, okay? It's radioactive means it's going to bring us another particle later, and because the nucleus is quite strange. They have too many neutrons. And from what we have learned before, the beta minus decay, when the nucleus is neutron rich, it's full of neutron. There are too many neutrons compared to proton. The neutron is going to be transformed itself to become proton. Okay, they just kick the proton, and proton is moving out and they stay here inside the nucleus. Now, nitrogen is transformed into carbon-14, but later neutron here is going to transform itself to become proton, but that takes time, like 5,730 years. Okay, half of the amount of the carbon-14 is going to reduce. Okay, and to disappear. Okay, and this happens in the upper atmosphere, like 9 to 15 kilometers above the ground. Okay, you just measure from the elevation, the sea level, by 9 to 15 kilometers. I think it's in the area of your airplane flying, right? Flying layer. Okay, in that elevation, the cosmic ray just take this reaction process for neutron to become, for nitrogen to become carbon-14. So carbon-14 stay on our atmosphere, and it could move downward to us on Earth, and we breathe the carbon dioxide into our body, and carbon dioxide, carbon will stay inside our bone, or even the plants. The plant consume the carbon dioxide in the version of carbon-14, which is radioactive. The plant would have also carbon-14 inside the trees in their body. And because human eats also plant, vegetables, the cow eats, has the gases, right? The gas from carbon-14. So the meat of the cow, the meat of pig, the meat of several kinds of animals will be full of carbon-14 too, right? And human like us are eating those kind of meat, right? So carbon-14 will get into our body. How many years you live, you would collect carbon-14 in your body, and that's the thing that happens. Okay, in the atmosphere 9 to 15 kilometers above the ground, we have the upper layers like troposphere and stratosphere, and that's the layer of the atmosphere where this process, equation say the one that took place. Okay, the generation of the carbon-14 is not man-made, it's made by nature. From cosmically, we have to say thank you. We have to say thank to the scientists who first found this one. Okay, the ratio of the carbon-14 to the carbon-14 nuclei to carbon-12, which is the typical carbon, is constant. Okay, approximately 1 by million. Okay, if you pick up a piece of carbon inside your body or everywhere on Earth, only one from 1 million candidates will be carbon-14. I don't know how to say it. It's even smaller than the number of population you could find on Earth, right? We have population on Earth like 7,000 or 10,000 millions on Earth, but this one is 1 from million people. Okay, 1 from million people is very, very rare. Okay, but still we have carbon-14 around 1 piece from 1 million pieces of carbon-12, okay, carbon candidates. But the ratio is constant. Okay, if you don't completely understand, just take a look at this. Okay, we arrive at the carbon dating, right? Okay. Yeah, as I told you, equation 71 take place during this process. You have nitrogen 14. Nitrogen is a part of our atmosphere, right? You know that the air is full of like 78 or around 80% of nitrogen, and some after that we have carbon. We have oxygen, right? Like 18 or something like that. Yes, Cosmic ray is the high energy protons and alpha particle. It's not, yeah. And some of them will release the nitrogen too, the neutron too. Okay, and once it moves from outer space, from other planets, from other stars, from the sun, from any source of high energy star, the protons and the alpha particle will hit our atmosphere. Okay, it doesn't come with neutron, but once it hits our atmosphere, the neutron is generated. Okay, many neutrons are generated, and neutron, once it's generated, it has also energy. The neutron will hit the nitrogen 14, okay, and it will kick out one proton. Okay, it will kick out one proton and it stay in place of that location, of that proton location. All right. And now we got carbon 14, okay, losing a proton and gaining a neutron. It changes nitrogen 14 to become carbon 14, okay, because we reduce the number of protons by one, we get a small element from this one, right? Nitrogen to become carbon, okay, we reduce the number of protons by one. We don't need that, but it takes place in nature, okay, and yeah, once the carbon stay inside our atmosphere, it can interact with the oxygen, right? Oxygen is another element that could stay inside our atmosphere, right? Our air. And two pieces of oxygen will bring us to carbon dioxide. Okay, they stay together by chemical bonding, right? Carbon dioxide or carbon monoxide, okay, get oxidized also into carbon dioxide. And we have plant right on Earth. This Earth, the planet that has plants. Okay, the plants will consume, okay, will take carbon dioxide into their chlorophyll process and so on, and they will have the carbon dioxide, which is the 14th version of the carbon inside their body. Okay, and the animal like cow, pig, and other pets will take the plants here, and so carbon 14 will stay inside the body of animal. And once the human are hungry, when the human is hungry, they just take the meat from cow, beef from pig, and so on. Okay, chicken and so on. So carbon 14 will stay inside our body too. Unfortunately, we cannot avoid that. Okay, the formation of carbon 14 from the cosmic rays and its absorption in the nature. This is the whole process. And that's the whole thing that happens in nature. But for us in physics, we're going to analyze it. Okay, formation of carbon 14. Okay, and this is the generation, and right here. Okay, generation right here. Generation of the carbon 14, this one. Okay, neutron will hit the nitrogen nucleus. Okay, and you see that there are 7 protons, the red one. Okay, the red one, and we have only 6 protons right here because neutron hit the proton and proton is going out. Okay, proton is getting out of the nucleus, unfortunately, and we have only 6 protons. And now the atmospheric nitrogen is no longer valid. It becomes carbon 14. Okay, yeah, that's the generation of the carbon 14. But once the carbon 14 stay everywhere on Earth, whether inside the stomachs of the pets, whether inside the plant, whether inside our body, it will try to change itself to become nitrogen 14 because this one is more stable. Okay, the nuclear force inside the nucleus is better, so carbon 14 is not good. Okay, it's not in a good state. carbon 14 will change itself to become nitrogen 14, which is back here, the original version in 5,730 years. Okay, if you have two pieces of carbon 14, it's gonna remain as one carbon 14, and one become nitrogen 14. Okay, half of that will be converted to nitrogen 14. And during this decay process, what is the problem? And of course, you know that carbon 14 has too many neutrons, right? Because it's throw away one protons. They have too many neutrons. It's neutron rich, and neutron will be converted to 4, 6, 8, right? 4, 6, 7. Okay, neutron will be converted itself to become proton. Okay, so that the element now changes from carbon to nitrogen. One more proton is generated, and this process is beta mass, right? And it's going to bring you one electron. Okay, electron will get out of the nucleus of the carbon 14. Okay, and the nucleus remains as nitrogen. And one more thing, as you completely know before, we will have also the Electron Anti-Neutrino. Okay, sometimes they write down with E, sometimes they write down without E. Okay, and that's the thing we know completely from the beta minus decay. Okay, because we found that the energy of this one is too big. Okay, from the pure calculation. So Wolfgang Pauli believed that there should be another particle apart from electron, and that's called that is known by Fermi. I think he said is neutrino, right? It's neutral. It has no charge, but is very small, right? So neutrinos. But this one is not neutrino, it's electron anti-neutrino. Okay, it has no charge, it's very small, the mass is very small. This is the decay of the carbon 14. Okay, this one is the generation of the formation. Another way is another situation is that nitrogen is heated by neutron. We get carbon 14, and the proton is kicked out. And after that, the carbon dissolves. Okay, the carbon 14 changes itself to become nitrogen. Okay, this is the process that happens also in our body every day. Okay, and yeah, we got electron and electron neutrino, and this nitrogen will be back to the source in the upper atmosphere that receive the high energy neutron from the cosmic ray. Okay, the whole process will rotate like this, and yes, once you measure the quality of carbon 12 and carbon 14, if you live on Earth, the ratio between carbon 12 and carbon 14 will remain the same, because you exchange the breath on Earth, you eat the food and so on every day. So the amount of carbon 12 will be like a million times the amount of carbon 14 every day. Okay, every day. But once you die, okay, you pass it away. Once you pass it away, you don't insert the carbon 14 anymore to your body, because you stop breathing. You don't need to have the food anymore. Your body remains the same every day, right? And once that once that situation takes place, the amount of carbon 14 will be smaller, will decrease, will be reduced every day. So this is the condition of the idea of carbon 14 that happens in nature. Okay. Yes, and the human or the scientist or the physicist use this nature to estimate how long that object that lasts from the beginning or that it stop dying. Okay, it stop breathing or it start to die. Okay, all living organisms have the same ratio of the carbon 14 to the carbon 12 because they continuously exchange carbon dioxide with their surroundings. Okay, to breathe every day, you have carbon dioxide, and carbon 12 will be 1 million times the amount of carbon 14. Okay, but once we die, okay, our body no longer absorbs carbon 14 from the atmosphere because we stop breathing. Carbon 14 has already absorbed decay. Okay, the amount of carbon 14 will decay because carbon 14 is radioactive. They are going to change themselves to become nitrogen with electron and electron neutrino. Okay, this process will take place all the time, but you put also carbon 14 into your body, so it's gonna remain stable, balanced here. But once you stop breathing, okay, this process, the input will not take place. The carbon will reduce itself every day, so the amount of carbon 14 will be smaller in your body or in any object on Earth, or especially in the creative living thing. Yeah. So the ratio of the carbon 14 to carbon 12 will decrease every day as a result of the beta decay by carbon 14. This is the beta decay, right? Beta minus decay. We got the electron. By measuring the portion of carbon 14 in the remaining stuff, we can determine how long ago that object or organism died. Okay, we cannot make the carbon dating to stone or some dating. We would make the carbon dating to only the living or the organism. It is possible to determine the age of a material by measuring its activity per unit mass. As a result of the decay of carbon 14, okay, you measure the amount of carbon 14 atoms per 1 gram or something like that. Okay, and that's the way you can observe how long that organism has passed away, has died. Okay, okay, the one example is the following. เราเท่าไหร่นะ16.0ใช่ไหมเราต้องจบที่15.40ใช่ไหมครับก็จะประมาณ26 นาทีครับประมาณครึ่งชั่วโมงนะครับโอเคthis question just arises from the book number 1 in example 30.4, the activity of the atmospheric carbon of the presence of due to the presence of the carbon 14 is about 0.255 becquerel. Okay, so becquerel is the basic unit, right? It's not Curie. Becquerel per gram of carbon. So the rate of change of okay, the absolute delta N by delta T, right, is 0.55 nuclei per second per gram of carbon. So what fraction of carbon atoms are the carbon 14? So we are going to find a fraction of the carbon 14 in that object. Okay, and if the activity of archaeology specimen, so we are interested in some organism piece or stuff, and we found that the activity of that specimen that piece is 0.0637 becquerel per gram. What is approximate age to that? Okay, so we would start to calculate the activity of this one in the following. Okay, now we need to talk about the mass of the Avogadro number of the carbon 12 isotope. Okay, you have to get back to the chapter of heat and so on in our in heat and gas chapter, okay, which is in the previous semester. Okay, in the previous semester we have the chapter of heat and gas, and one of the story is the Avogadro number, which is the number of atoms per mole, right? So Na is the Avogadro number, which is 6.022 10 to 6.022 times 10 to 23, which is very large. Okay, in 1 mole of element, okay, measurement way in chemistry and also in physics, right? There are like 24. What is that? 23 is million-fold, almost 4 times. Okay, million atoms per mole. Okay, you can count the number of atoms like that. And yes, the carbon-14 would last 12 atomic mass unit per atom, and we would have 1.660538. This is the mass of the carbon per gram, right? This is the mass in terms of gram per unit mass, okay? And yes, of course, in 1 mole, we would have 6.022 million 4 times, almost 4 times, times 12 and times 166. Okay, we have exactly 12 grams per mole. So the mass of the carbon 12 is 12 grams per mole. Okay, that's exactly the same way. Okay, because we use carbon 12 as the reference, okay, in order to create the atomic mass unit. In a standard, carbon 12 is approximately subject to 12 grams per mole, okay, and the carbon 12 with the mass of 1 gram is equal to only 1 gram, okay, is equal to 1/12 mole. So in 1 gram or 1/12 mole, the number of carbon 14 will be 1/12. Okay, please say that. Yes, the number of carbon 14 will be 1/12 of the number of the Avogadro number. So 1/12 of 6.023 times million, almost 4 times, will be 5.018333 times 10 to 12 atoms. So we have this number for the carbon 14 atoms in 1/12 mole. So the number of carbon 14 atoms can be computed from this one, right? From the decay process, right? Is -1 by lambda delta n by delta t. And we know that lambda is ln2 by half-life, right? Lambda is the decay constant, and it's going to be negative because the number of atoms the number of nuclei or the number of atoms will be reduced. So it's negative, right? The rate of change is negative. So we have the rate of change is negative, become positive. So this one, the decay constant is ln2 by half-life, and delta n by delta t is the rate of change of the nuclei per time, which is the activity actually. So the activity is known as 0.255, right? Becquerel means 0.255 nuclei will decay per second. So this one is minus 0.255, but half-life is 5,730 years. So you have to convert everything into SI system. SI system means the time should be in the second, right? The time should be expressed in second. It's 5,730 years and 365. Okay, we convert years to second, right? The half-life of the nitrogen of the carbon 14 here is 5,730. We have to multiply 1 year by 365 days, and in 1 day we have 24 hours. In 1 hour we have 60 minutes. In 1 minute we have 60 seconds. Okay, and that's the half-life converted to 2 seconds, and still we have ln2 as the denominator. Right here, negative stay in front of that. And the rate of change is the value that the problem has provided, 0.255. But you need to know that the rate of change should be negative because the nuclei disappear. Okay, the number of atoms or nuclei will reduce. Okay, they are not gonna have more. Okay, they're gonna stay more. Okay, it will disappear. So these numbers should be negative. So that's why we have 0.255 decay per second. We don't substitute it by positive value because it means your nuclei is going to increase itself by 0.255 nuclei per second. But it's not the case because carbon 14 will disappear according to this process here. Okay, the beta minus decay process. Okay, carbon 14 will disappear. So we have substitute the negative values to 0.255 decay per second into this one. Okay, and after the calculation, you put everything into the calculation. The number of carbon 14 atoms or nuclei. Okay, once we say the number of atoms or nuclei will be the same. Okay, because when you say atom, it means it stays together with appropriate electrons, right? Okay, so the number of carbon 14 will remain 6.6 times 10 million, 10,000 million atoms. Okay, it's very, very large. But the number of carbon 12 will be right there. Okay, one. Yes. Now we compute the ratio between carbon 14 and carbon 12. Of course, carbon 12 will be 5.018, which is what we oh, I'm sorry for that. This is อันนี้ก็ผิดนะครับเดี๋ยวแก้นะ Oh, I'm sorry for that. This number is number 2. Okay, again ผมก็ว่าแล้วมันดูแปลกๆ and this one too. This one should be number 1. Okay, this one พิมพ์ผิดนะครับ okay, this one will be carbon 12, and this is the amount of carbon 12 we got from the only part of the Avogadro number, right? We divided Avogadro by 12. We got this one, and this is the carbon 14, which is computed from the decay process. And we take the ratio between carbon 12 and carbon 14 and carbon 12 in terms of nuclei or atoms, right? We get the ratio. It's on the order of 1 million pieces of carbon 12. Okay, you could find one piece from this 1 by 3 million candidates of carbon 12, and yes, this is the ratio. So the rate of change by the specimen is 0.0637, which is this value. Okay, they say the activity of the rate by the specimen is 0.0637, but the rate by carbon 14 is 0.255. Okay, this one. Rate of carbon 14 is this one. Rate of any object is this one. Okay, any piece of interesting object, and you just take the ratio, and it's going to be 0.249 or 0.25. Okay, 1 by 4. Rate of change, rate of disappearing rate at that moment is 0.673, but for carbon, usually it should be 0.255. So what does that mean? We are gonna compute how many how long does it take, right? Lambda n is equal to n01 by 2 with the power of n. And the left-hand side is the rate of the specimen of any pieces. And on the right-hand side, it's going to be rate of carbon 14. And we move the rate of carbon 14 to the left-hand side. The rate of this one will be, okay, of course, this is 1 by 2 is going to be negative, T half, right, half-life. And our specimen by R14 will be this ratio. And this ratio, it has been computed before, which is 0.49, 0.25. Okay, we leave 0.249 or 25 right here on the left-hand side. Approximately, okay, because this is the approximation. And yeah, once we take the logarithm to logarithm function to both sides of this equality, this relation, we get the T by half-life on 2, right? And we want to find time, okay? We want to find the time, how long does the specimen last away, passes away. Yes, we take the logarithm and we get T by T half-life. And we're going to solve this one for small t. Okay, we move half-life to the left-hand side. We move log 2 to the left-hand side. We move negative to the left-hand side. We get this one. Once you get this one, we will substitute the half-life of the carbon 14. And it's up to you. If you want to find, if you want to see the result in second, you have to convert half-life from years to second, multiplying by how many days per year, how many hours per day, how many minutes per hour, how many seconds per 1 minute. You have to multiply. But if you want to find the result in the scale of years, you don't have to convert half-life to be second. Okay, just leave it like years in the year scale. So once you substitute 5,730 to this ratio, we are going to have result as 11,466 years. So that object, that specimen has started to die 11,466 years ago, approximately, plus and minus 40 years. Okay, so it's order of 10 million years before. Okay, and that's the age of that object, around 11,000 years ago. Okay, yeah, the scientists or the physicists use this idea to find the date, find the age of that object. Okay, based on the number of carbon 14 particles or atoms or nuclei. All right. Yeah, one thing in carbon dating is that one difficulty with radiocarbon dating is that the concentration of the carbon 14 in the atmosphere nowadays has really quite a lot, because in the past 100 years ago, in the past 100 years, the human has used so many cars. We burn oil, we burn fossil, we burn natural gas, so that carbon 12 will take place easily in our atmosphere, right? When you increase the carbon 12, so the ratio between carbon 12 to carbon 14 is going to be changed. It's no longer in the same ratio as 100 years ago, because we start to have vehicle, we have automobile, we have cars, we have many factories that burn the fossil every day. So the carbon 12 amount will change, and this will cause the ratio between carbon 12 and carbon 14 to another value. Okay, and one of the things is we have tested the nuclear weapons. So nuclear weapons will cause the amount of carbon 12 and carbon 14 in a different way. So the carbon dating might not be valid in this generation, 100 years since human start to consume or burn the fossil. Okay, correction can be made on the basis of other data. What is other data? You may use another isotope like potassium or other elements that have also that sufficient amount in the object, like potassium or other element, I cannot remember, calcium too, right? Yeah, this is the thing that happens. I could not do anything, okay. The next one is the nuclear reactions. We still have 19 minutes, right? We still have 19 minutes in. Okay, nuclear reaction. Okay, sorry for that. I need to show you where are we right now from the beginning of this chapter. Okay, we are here. Okay, we have finished the carbon dating. Okay, we finished the carbon dating. We start the nuclear reaction, which is taken from book number 1, section 29.6, or book number 2, section 30.5. And next one, we're going to talk about nuclear fission and nuclear fission. And we go to the next section of this chapter, which is particle physics. Actually, nuclear reaction, nuclear fission are really very close to the particle physics already. Okay. And even the carbon decay rate, alpha decay, you have been involved with electron neutrino, you have been involved with electron neutrino. That's also the stuff about particle physics. But anyway, we will go to nuclear reaction, which is the basic thing you need to know once you study physics in high school or in the college level. Okay, we have seen several decays of unstable nuclei in terms of emitting alpha particle, beta particle, right? You have seen here alpha decay, beta decay. And sometimes once the nuclei are not in the stable state immediately, they are going to emit the gamma ray, which is a kind of high energy photon, right? Yes, that's the whole thing that takes place in nature. We could not control, we cannot do anything. The human just learn what takes place around our life, right? We just try to understand what happens in our environment. But for the human made, what is the process then? Okay, let's consider another aspect. When the human try to have the nuclear process like beta emission, alpha emission by ourselves. Okay, nuclear reactions are the changes of the nuclear structure by bombarding them with energetic particles. What is that? It means it's human made, okay? It's a purpose by human. Alpha particle from radium to radon and helium-42 just take place by nature. We didn't force them to happen, but it just happened in nature. Okay, from neutron to become proton, it just takes place by nature. The gamma ray and so on. The cosmic ray that causes carbon-14 too. Okay, it's in nature. We cannot do anything. Cosmic ray come from outer space. We cannot force anything. But the process that human try to force to take place is the following: the human accelerate a particle and project it to a nucleus, and we get a new nucleus. Okay, in 1919. Rutherford, you know Rutherford, right? Rutherford is the main person who observed something about isotope or radioactive element. In today is 2022, right? It's around 103 years ago. Okay, 100 years ago, Rutherford bombarded nitrogen with alpha particle from naturally radioactive force. Okay, he got alpha particle. So alpha particle is the method that Rutherford asked his student to observe, right, project the alpha particle to the thin gold plate, right? And they wanna observe the electron orbits, right? And they try to make the model of the atom, right? But beyond that, Rutherford made another type of experiment. He accelerated the alpha particle from any radioactive force, and he let the alpha particle project it or hit the nitrogen 14 again, okay, nitrogen 14. And what is going out? And the result is that he got one proton, okay. X11 means the helium nucleus or hydrogen nucleus, sorry, which is actually a proton, right? Because the basic helium doesn't have neutron at all. So this is actually a proton. So Rutherford project the alpha particle to nitrogen nucleus, and he got oxygen, which is oxygen and hydrogen in a proton, right? And this is the first process, which is called nuclear reaction on Earth, okay, in 1919 by Rutherford. And once this experiment is spread away, okay, throughout the world, many people start to start this idea, because at that time, if you can have gold, right? Gold is a precious metal, right? They want to change the element to become gold so that you can get money, you can live with, and so on. So many people try to accelerate some other types of particle to hit any nucleus so that they can obtain a new particle, new nucleus, right? But nowadays, we still follow the way by Rutherford, because in a big laboratory in Switzerland, CERN, they have the particle accelerator. Okay, they and you know when you study this subject, this chapter, nuclear physics is known as high energy physics too, because we need to accelerate the particle so that it has high energy. When it has high energy, it hits. Okay, a high energy movement means the kinetic energy. Okay, when it hits at the nucleus, you could get something else. Okay, it's a kind of experiment. Okay, the idea by Rutherford is the starting point for human to build up big project of the accelerator, which still remain nowadays in many laboratories on Earth, in the United States, in the Switzerland, and so on, right? Okay, we don't go into the particle accelerator. Okay, we will talk about nuclear reactions solely, because we arrive at the topic of nuclear reaction. If the initial particles A and B, okay, this is this input side. If we start like this one, okay, this is the particle A, this is particle B. If the input side are A and B, and A and B are accelerated with high speed, and they crash each other, the nucleus of nucleus A, nucleus B crash each other, and they build up two new nucleus. The output is known as particle C and particle D. Okay, let's say this one. The reaction energy, which is the term we are going to concern, is given by this one. Okay, you have to convert the mass of the particle A, the input side. Okay, you have to know the mass of the input side at the same time with the mass B. And you make the subtraction to the mass of the outcome. The first mass is MC, the second mass is MD. Okay, just find the difference between mass at the input side to the output side. And the mass here is in the same way as the binding energy. Okay, but this one is not known as binding. Q is actually delta M C squared, which is the well-known formula by Albert Einstein, right? EMC squared or E delta MC squared is the way to convert the mass to the energy, right? And the mass is the most packed version of the energy. Okay, it's not electric energy. Mass is the the best way to pack the energy, because you can get much more energy from any little value of mass. Okay, let's get back to our story. Reaction energy is the difference between mass at the input side to the mass at the output side, and you calculate or you multiply it by c squared. But we don't do that actually, because we are going to use the simpler version. We're going to use the fast version, 931.5 mega electron volt per atomic mass unit, right? This is the general version. You can use it in the SI way, right? You can substitute here 3 times 10 to 8 and square and blah, blah, blah. But it involves a lot of complexity. We will not do that. Okay, we use the simpler version. Okay, let's talk about eddy. What happens to eddy? If the mass on the left-hand side is greater than the mass on the right-hand side, it means we have the positive value of the Q, because the left-hand side is the mass on the left-hand side is greater than the mass on the right-hand side. So the total mass decreases and the total kinetic energy increases. Okay, when Q is positive, of course, A and B are accelerated with high speed, right? And once they crash down, they build up 2 new nucleus. They have also kinetic energy. They would move, but they would say when Q is positive, the total mass decreases. So the summation of the mass C and mass D is less than the summation of mass A and mass B. And once we lose the mass is converted to energy, and Q is positive. These two particles will have more velocity or more kinetic energy, okay, when Q is positive. In the opposite way, if the mass on the right-hand side turns to be greater than the mass on the left-hand side, what does that mean? It means we spend some energy to the left-hand side and the energy transform into mass on the right-hand side. That's the case when Q is negative. When Q is negative, the total mass increases. So on the right-hand side, we have more mass than the left-hand side. And once it becomes bigger, okay, the mass is bigger, they kind of move well. The total kinetic energy decreases too, okay? They don't have as high as speed to the left-hand side at the input side. Okay, and we are going to say some word to this process. The first one, okay, both are still nuclear reaction, okay? This one is the Rutherford nuclear reaction. ภาษาไทยเรียกว่าปฏิกิริยานิวเคลียร์ประมาณนั้นครับ Okay, let's talk about the name for nuclear reaction. The first one, when Q is positive, we call exothermic reaction. Okay, if you are gonna study physics, okay, you need to know this word. Okay, it's not familiar. I'm not familiar with these two terms. I am not from the Department of Chemical Engineering. I'm not expert in this. Okay, the former reaction when Q is positive is known as exothermic reaction. This is the word in physics. Okay, exothermic, because physics pay attention to energy, power, speed, or something like that, right? So ergic energy are from the same root. So exothermic means Q is positive. This is the physics word, the word in physics sense. But for the people in chemistry, they are going to call exothermic, because thermodynamic is the main stuff for them. Okay, thermal energy is the main stuff for chemistry. So they are going to call the same process when Q is positive as exothermic reaction. Okay, for us, it's exothermic reaction. But for the chemistry people, they're going to say exothermic. Okay, when Q is positive, you have to think about the mass difference. Okay, if mass difference is positive, the energy turns to be positive too. Let's talk about the second case when the mass get bigger. So the Q is negative. Q is negative is known endoergic. Okay, the endo and down. Okay, negative. Endo and down to going down, right? It's negative. Endoergic reaction. That's the word in physics. But for the chemistry people, they're gonna call endothermic reaction. Okay, both of these are nuclear reaction, but it can take place in the different way. When the mass is positive, or the mass difference is positive, or mass difference is negative. When the mass difference is positive, the Q, the reaction energy, is going to be also positive. When the mass difference is negative, the Q, which is the reaction energy, the energy from the reaction nuclear process, is negative. And the word in physics and chemistry are a little bit different, but they are very close to each other. Exoergic for positive Q, endoergic for negative Q. And for in chemistry, it's going to be exothermic reaction for positive Q, endothermic reaction for negative Q in chemistry society. Okay, now we arrive at the first example. We're gonna try to solve one problem regarding the nuclear reaction. We are talking about the nuclear reaction, right? Yes, of course. What time is that? Okay, I think it's better if we have the calculation next time. Otherwise, we will get stuck. Okay, because there are a pair of problems right here. Okay, the first example and the next example here. Okay, they are both a pair to each other. Or they are a couple of each to each other. So it's better to leave the calculation for next time. And I'm going to capture what's going on with you in M605 in your chat list. No one appears in the Zoom meeting, right? So we have to leave the lecture right now. If you have any question, just let me know, okay? If you have any question, just let me know. Then we will leave our lecture like this. สวัสดีครับ M605 นะครับ บ๊ายบายนะครับ พบกันวันศุกร์นะครับ calculation ตรงนี้คำนวณพลังงานปฏิกิริยานิวเคลียร์เดี๋ยวทำครั้งหน้าเพราะว่าถ้าทำค้างไว้มันก็ไม่ทันเวลาแล้วก็เดี๋ยวคุณค้างเพราะมันมีคู่กันอยู่นะครับ Q เป็นบวกกับ Q เป็นลบนะครับโอเคถ้ามีคำถามนะครับโปรดถามนะครับเดี๋ยวผมจะแคปหน้าจอนะครับเพื่อเช็คชื่อคุณนะครับบ๊ายบายครับสวัสดีครับ ลืมแจ้งครับเรื่องไปหมดแล้วลืมแจ้งเรื่องคะแนนข้อสอบนะครับคะแนนข้อสอบ605ผ่านหมดทุกคนนะครับก็คือเดี๋ยวผมแจ้งคุณครูโคนะเพื่อแก้คะแนนให้เป็น10 คะแนนครับSo we can stop right. Stop the meeting right now. So nothing on it.